Uh, in this session, we would be discussing about the 12th chapter, that is aldehyde, ketones and carboxylic acid. The topics we will be studying in this session would be the introduction to the chapter, nomenclature, and the structure of the functional group. So the introduction, the organic compounds containing carbon-oxygen double bond, that is organic compound like these, called carbonyl group, which is one of the most important functional group in the organic chemistry. In aldehydes, the carbonyl group is bonded to a carbon and hydrogen, while in the ketones, it is bonded to two carbon atoms. The carbonyl compounds in which carbonyl group is bonded to oxygen are known as carboxylic acids, and their derivatives, examples esters and hydrides, while in compounds where carbon is attached to nitrogen and to halogens are called amides and acyl halides respectively. Aldehydes, ketone and carboxylic acid are widespread in plant and animal kingdom. They play an important role in biochemical processes of life. They add fragrance and flavor to nature. For example, vanillin, which is from vanilla beans, we get it from vanilla beans. Salicylaldehyde from meadow sweet, and cinnamaldehyde from cinnamons have very pleasant fragrance. They are used in many food products and pharmaceuticals to add flavors. Some of these families are manufactured for use as solvents, that is acetone, and for preparing materials like adhesives, paints, resins, perfumes, plastics, fabrics, etc. So this is the structure of vanillin, salicylaldehyde, and cinnamaldehyde. These are typical aldehydes. These are typical ketones. This is carboxylic acid, acyl halide, acid, and hydride. Acyl halides have an halogen attached to it. Aldehydes have C double bond OH group attached to the alkyl chain, alkyl group. Two alkyl groups attached to, they can be same and different, attached to C double bond O group, ketonic group, carboxylic acid, C double bond O attached to OH and the alkyl chain, acyl halide, acid and hydride. So these are typical the compounds we will be studying in this session. So the nomenclature and structure of carbonyl group. Aldehydes and ketones. Aldehydes and ketones are the simplest and most important carbonyl compounds. There are two systems of nomenclature of aldehydes and ketones. The first one is common name and the second one is IUPAC name. The aldehydes and ketones are often called by their common names instead of IUPAC names. The common names of most aldehydes are derived from the common names of corresponding carboxylic acids by replacing the endic ic of acid with aldehyde. At the same time, the names reflect the Latin or Greek term of the original source of the acid or aldehyde. So in place of ic of the acid, aldehyde is used, and it also shows the compound it has been derived from. So the aldehyde from the acid. The location of the substituent in the carbon chain is indicated by Greek letters alpha, beta, gamma, delta, etc. The alpha carbon being the one directly linked to the aldehyde group, beta carbon the next, and so on. So if this is the aldehydic group, the carbon which is attached to the aldehydic carbon is alpha, the second one is beta, and the next one is gamma. The alpha carbon being these are the examples. We have acetaldehyde, we have benzaldehyde. So these are the examples. Common name of ketones are derived by naming two alkyl or aryl groups bonded to the carbonyl group. The location of the substituents are indicated by Greek letters alpha, alpha dash, beta, beta dash, and so on. beginning with carbon atoms next to the carbonyl group indicated as alpha aldehyde. Some ketones have historical common names. The simplest dimethyl ketone is called acetone. Acetone we use in daily uh, household purposes for removing paints and for various other purposes. Acetone is used. Alkyl phenyl ketones are usually named by adding the acyl group as the prefix to phenol. For example, acetone, we have acetophenone if we have the benzene ring attached instead of one of the carbon or alkyl chain. Propiophenone, because instead of acetate we have three carbons now. Benzophenone, because in both of the alkyl group we have benzene rings. So these are the common names of acetone of ketones and how they are derived and written. Now the IUPAC name. The IUPAC names of open chain aliphatic aldehydes and ketones are derived from the names of corresponding alkanes by replacing the ending E with ul and one. It is not one, it is known as un. Ketone, so it is known as on, respectively. In case of aldehydes, the longest carbon chain is numbered starting from the carbon of the aldehydic group, while in case of ketones, the numbering begins from the end nearer to the carbonyl group. The substituents are prefixed in alphabetical order along the numeral indicating the position in the carbon chain. So in ketone, the ketonic group is attached in the middle. So what we do is we number the carbon from where the ketonic group gets the least number. Whereas in aldehydes, we give the priority to the carbon of the carbon which is attached to oxygen and hydrogen, the carbonyl carbon. So that is given the foremost priority, that is 1, and the others are given along with the second, third, etc. So the numbering is like that in ketones and aldehydes. The substituents are prefixed in alphabetical order along with numeral indicating their positions in the carbon chain. The same applies to cyclic ketones, where the carbonyl carbon is numbered 1. When the aldehyde group is attached to a ring, the suffix carbaldehyde is added. So carbaldehyde is added when it is attached in a ring. For showing a ring, we write carbaldehyde. Is added after the full name of the cycloalkane. The numbering of the ring carbon atoms start from the carbon atom attached to the aldehydic group. Again, we give the priority to the aldehydic carbon. The name of the simplest aromatic aldehyde carrying the aldehyde group on a benzene ring is benzene carbaldehyde. So carbaldehyde is for cyclic compound. So benzene carbaldehyde. However, the common name of benzaldehyde is also accepted by IUPAC. So in case of benzene carbaldehyde, we also use benzaldehyde as a common name. Other aromatic aldehydes are hence named as substituted benzaldehydes. So if we have ethanol, we have 4-bromo 3-methyl heptanol, because 1, 2, 3, 4, 5, 6, 7, the longest chain, that is hepta. We have the carbon, the aldehydic group on the first carbon, and on the third carbon we have the alkyl group, methyl group, and fourth carbon we have bromine, bromo group. So the methyl comes after, the bromine comes before methyl, or methyl comes after bromine according to the alphabetical order. So 4-bromo 3-methyl heptanol. So we do not number, we can number actually the aldehydic group as heptane 1-ul, but heptanol can also be written according to IUPAC nomenclature. For the cyclic compound, this is a ketonic compound, as there are both carbon attached to the ketonic group. So it is also known as 3-methyl cyclopentanone. as we have to get the highest number of carbons. So 1, 2, 3, 4, 5, 6. So 3 methyl, we have to give the least number to the carbon containing ketonic group. So we write 1, 2, 3, 4, 5, and the first carbon has the ketonic group, so we do not name it as pentane 1 on. We write 3 methyl, as on the third the branching of methyl is there, so 3 methyl cyclopentanone. We start the counting from here instead of counting from here, because it will give a very great number to the ketonic group. The next one is cyclohexane carbaldehyde. This is again simple, a cyclohexane and carbaldehyde attached to the first carbon of the cyclohexane group. Next is pentane 2-enol, because we have pentene here and we have the aldehyde group attached to it, 5 carbons with an alkene with a double bond. The next is 1-phenyl propane 1 on, because 1-phenyl and propanone. So this is 1-phenyl propanone, and this is the IUPAC nomenclature of the aldehyde and ketones. This is another example, oxopentanol, where we have both ketone and aldehyde on the same chain. So 3-oxopentanol, 1, 2, 3, 4, 5. We give the priority to the third carbon, to the aldehyde group. So 3-oxopentanol. Now this is, we have the same groups. So we'll count 1, 2, 3, 4, 5. We get third number on the ketonic group. So it is written as 2,4-dimethyl pentane 3 on. Similarly, this is 4-nitrobenzaldehyde or 4-nitrobenzene carbaldehyde. This is propane 1,2,3 carbaldehyde, as on each carbon we have a aldehyde group. So to give identical treatment to all aldehyde groups, the compound is known as shown above. So this is how they are shown, to give identical treatment to the aldehyde group, since all the aldehyde groups are same. So it is known as 1,2,3 tricarbaldehyde instead of 1,2,3 propane 1,2,3 we write propane 1,2,3 tricarbaldehyde, because all the carbaldehyde groups are same, and we do not include them in the main chain because it is propane 1, 2, 3 propane, and we have all the 3 groups attached to them. So we do not write 1, 2, 3, 4, 5 pentane 2 pentane 3-al or etc. So we write propane 1, 2, 3 tricarbaldehyde. These are the common structures, their common name and IUPAC name, out of which formaldehyde is widely used. Its formula is HCHO and IUPAC name is methanol. The next one is CH3CHO. Its common name is acetaldehyde. IUPAC name is ethanol. The next one is CH3CHCHO, isobutyryldehyde or 2-methylpropanol. The next one is this. So gamma methyl cyclohexane carbaldehyde or 3-methyl cyclohexane carbaldehyde. Similarly, there are other aldehydes and ketones present here. So these are of very much importance and should be read carefully. Ketones, this methyl group on one side, and on the other side we have a propane group. So the common name will be methyl normal propyl ketone, and IUPAC name would be the longest chain is pentanol, and on the second carbon we have the ketonic group, so pentane 2 on. The cyclic group, we have on the alpha carbon we have methyl, so we write alpha methyl cyclohexanone, and this is an alkene. Its common name is mesytyl oxide or 4-methyl pentene 3 pent 3E2 on. So these are the common structures and their names. Now the structures of the carbonyl group. The carbonyl atom is sp2 hybridized and forms 3 sigma bonds. The fourth valence electron of carbon remains in its p orbital and forms a pi bond with oxygen by overlapping with the p orbital of an oxygen. In addition, the oxygen atom also has two non-bonding electron pairs. Thus, the carbonyl carbon and the three atoms attached to it lie in the same plane, and the pi electron cloud is above and below this plane. The bond angles are approximately 120 degrees as expected of a trigonal coplanar structures. So this is how they are bonded, the pi bonds, double bonds. The carbon-oxygen double bond is polarized due to high electronegativity of oxygen relative to carbon. Hence, the carbonyl carbon is an electrophilic, that is Lewis acid, and carbonyl oxygen is a nucleophilic, that is Lewis base center. Carbonyl compounds have substantial dipole moments and are polar than ethers. The high polarity of the carbonyl group is explained on the basis of resonance involving a neutral, that is A, and dipolar structures B. So that is the reason why the carbonyl structures have polarity due to the difference in the electronegativity. Oxygen being more electronegative have more electron density, and carbon being less electronegative have less electron density. So if the groups attached to carbon are electron withdrawing group, it would destabilizes, in the unstable compound would be formed, and if they are electron donating group, then this carbon would get stabilized. So this is the structure of carbonyl group, and this is the end of this session. For more information, log in into Webcoach, and you can also refer class 12th NCERT textbook for further information. Thank you.